To study how mathematical thinking develops, the research team began by asking, how might children solve problems that use mathematical ideas before the procedures to solve them were formally introduced in school? Towers. Students were asked to select from stacking cubes of two colors and assemble towers of a given height.
We have 16. Don't look at ours.
This problem is from a branch of discrete mathematics called combinatorics, which is usually taught in high school or college as part of probability. Towers would become one of the central activities of the study.
The towers problem is a nice introductory counting problem because you don't really need to know anything to start it.
3, 4, 5 reds and 5 yellows.
1, 2, 3, 4, 5.
I only have 4.
Okay.
Okay, we'll stand them up straight so we know what we have.
The students were asked to attack the problem in their own way, and the researchers simply recorded what they did.
All right, then let's do one of these.
Yeah, I know. What we can do is we just put one on the top. See? Ta-da!
At the end, whatever strategy they used, the students would have to justify their answers and convince the others that their thinking was correct.
When a decision was made that students ought to be challenged more in their thinking about math, that it shouldn't just be rote computation, memorization, the interest on our part was to see what was possible, because we didn't know. And the driving question for us was to see how particular mathematical ideas developed. We chose key mathematical ideas that made sense because it wasn't too far away from what ultimately we would expect kids to learn in school.
White, blue, 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 blue.
The vision was for the students to be successful. And success, and I think that's still true today, but certainly it was at that time, was to be successful in algebra. Algebra is the first great separator. Students don't succeed in algebra. They usually don't continue their study of mathematics. And then that's a path for them. They don't go on in an academic track, and so they're eliminated from other programs as well. So we were interested in the beginning of algebraic thinking.
Do we have one like this but only a white on the top? 4 blues and a white? Mm-hmm. Oh, I got it. I got the 4 blues.
I'm about to white.
Oh God, this is a lot. No, wait.
The researchers found that after the students tried creating random towers, they quickly switched to using more sophisticated approaches, like pairing towers with opposites.
Can you tell me what you're thinking about?
Well, once when we find one, we just do the opposite of it.
What do you mean the opposite?
Like, when we found this one out,
Yeah.
we just put 2 blues on the top and 3 whites in the middle.
Oh, do they always have an opposite?
Yes. Yeah. Well, not. Yeah.
Towers is my first memory. It seems like we've been doing towers since I was about 8.
2 blues, 1 white, 2 blues.
Back then, I thought it was pretty much fun. I enjoyed building little towers. It was very childlike, but I really pretty much had more fun than thought of it as math.
Ain't the same. Those 2 are. Oh.
We called ourselves your guinea pigs.
This one better fit in there.
Well, give me some of these white and blue in case I find them in there.
We thought you thought that we were smart.
I mean, something with 3 here.
And when you came up, I thought you just wanted to experiment to see what our capabilities were. And that was very scary when you're young because none of us had any confidence.
Let's see if we have some of the same.
Let's put the sames in order.
No,
Hey,
I mean,
wait.
like, some
Right
of them.
here.
Well, some of them could be the same, right?
Oh, good idea.
This one,
This one. This one matches with this. Put the pairs, like the opposites.
Stephanie and Dana used a strategy of making pairs they called duplicates.
We just did one. We just did this one. And here's the duplicate, say.
What do you mean by duplicate?
Well, it's not the duplicate, but it's the upside down version.
This one goes to this one.
We were
And then
just
we turn
fooling
it back
around when we
down,
came.
And it does
It
that.
does that, say?
So it's not actually
The same, but when it's turned upside down, it's the same.
It is the same.
So is that how you did all of these?
Most of them, yeah.
Most of them? Show me another.
The only one we couldn't do it with
We had
was
certain ground rules in our research
this
because we
one.
were trying to study the development of mathematical ideas. But there were consequences of what we were doing. We said we would not show them. We didn't intend to show them how to think about a problem. That was not in our set of rules for being researchers. We did not believe that if they worked on a problem for 1 or 2 hours, now that when they were all finished, we had to tell them if they were right or wrong. We didn't have to follow that rule. We could say, well, maybe you need to think about that some more. We've been interested in creating conditions whereby we can give children an opportunity to show us how they think about mathematics. So the only thing we're doing is making conditions possible. The children are doing the rest. Okay, you're all convinced you can take a stranger and tell them there are no more, right? Now, remember I walked around and you were convinced because you worked so hard doing this problem. Remember, you really worked hard. I don't think I've ever seen a 4th grade class work so long on a math problem ever as you worked without stopping. You're incredible. I think you're great. Let's give you a round of applause.